I'd like to welcome everyone today to the third part of our webinar series, Deep Row Entrenchment of Biosolids Using Hybrid Poplar. This is a three-part series, as I said. My name is Andrew Kling with the University of Maryland Extension Woodland Stewardship Education Program. If you haven't joined us for the previous webinars on October 30th and October 20th, they are going to be available through our website, but I'll tell you a little bit about what we've covered already. We introduced the subject on October 13th with the program, Why Am I Here? What You Need to Know About Deep Row Entrenchment, DRE, of Biosolids Using Hybrid Poplar. We followed that up last week with the nuts and bolts of the DRE technique, the importance of getting it done right. And we're wrapping things up today with protection of water quality and monitoring options for DRE. But before we turn things over to our speaker today, we have a little bit of housekeeping to take care of. First thing, I want to let you know that this webinar is being recorded. And by joining us today, you're giving us permission to take care of all of the things that have to do with recordings, including using your chat room comments. And as I said, the recording will be available through our website at go.umd.edu/woodland. If you scroll down the homepage, you'll find the webinars and videos category, and that's where you'll find this webinar series and its recordings. Now, when you come into a University of Maryland webinar, your microphone is muted and your video is turned off. And please, we'd like you to make sure they stay that way. That makes everybody's participation much more optimal, makes things easier for everyone. If you have a question or a comment, please use the chat box at the bottom of the screen. If you're new to Zoom, it's that little icon down in the middle that looks like a cartoon or a comic strip bubble. If you're not new to Zoom, you know exactly what I'm talking about. Now, today's speaker is Gary Felton. Gary is Director of Extension for the Environmental Science and Technology Department and has served as the Extension Water Quality Specialist at the University of Maryland. He received his bachelor's and master's degrees in agricultural engineering from the University of Maryland and his PhD in agricultural engineering from Texas A&M University. He's been working in non-point source pollution, focusing on urban nutrients since 1978, and he's worked in biosolids since 2005. So Gary, if you're ready, I will go ahead and stop sharing my screen and mute my microphone, and I'll turn things over to you.
And I'll get mine up just as soon as I can. Just check, Andrew, is my voice coming through and is my screen good?
Everything looks good. Go right ahead.
Okay, fasten your seatbelts. We're going to talk about water quality basically today. Whenever we talk about DRE, we're talking about putting a whole lot of nitrogen out on the ground. And that's a great concern to a lot of people, and we'll talk about it. This is our bulletin that we've shown you 2 other times. There's a link to the website where you can download this bulletin. Make sure that you have a reasonably fast connection. There's a lot of pictures in here. And this is an overview of where we're going to try to go today. I'm just going to quickly mention the environmental benefits of DRE, talk about monitoring a lot. Just a few mentions of things, experiences with permits, and then I'll try to quickly summarize where we are. When we talk about environmental benefits, these are just some of them, but it improves wildlife habitat because there's trees there, and there's not as many trees as there used to be. It creates carbon sequestration by the roots underneath the surface, increased infiltration and decreased storm runoff, which is something we're really worried about in the Chesapeake Bay watershed. Extends the life of landfills because people do put biosolids in landfills still. And it can be used in reclamation to reclaim mines, not just coal mines, but reclaim mines. If you look at our Erko site, it's actually a reclaimed sand and gravel mine, and we'll come back to that site now and then. Basically, we're talking about this hole in the ground with biosolids put in it and covered over and trees planted on top of it. Beneath the ground, the things you don't see going on is that there's no oxygen in the biosolids. The water content when you put it in there is about 75% water in the biosolids, and that's fairly well contained within that trench for a while. It's a lower water temperature, around 54 degrees Fahrenheit. So that's a little cooler than the 88 degrees it is at the ground surface. The nitrogen activity slows mineralizations. Denitrification can take place longer. Roots provide oxygen when the roots get to where they're going, and there is nutrient uptake by the roots. That's DRE in a nutshell. First off, it's not all that deep. When you look at a sketch of DRE, what we're looking at is something where the bottom of the trench may be around 48 inches. The trench is 42 inches wide because that's how big the special backhoe bucket was that was ordered for this project. And there's overburden on top of the biosolids in the neighborhood of 24 to 30 inches of overburden. And then that whole thing is flattened out so that it can be planted on. So this is what we mean by deep row. It's just not all that deep. This is a high nitrogen application, somewhere between 170, or corn is somewhere between 175 and 200 pounds of nitrogen per acre, and the DRE applies 172 to 345 dry tons of biosolids per acre. Note, I just changed units from pounds of nitrogen to tons of biosolids. It's about 3,400 pounds of nitrogen for each percentage of nitrogen on a dry weight basis in the biosolids. So that ranges, depending on the biosolids, somewhere between 4,000 and 15,000 pounds of nitrogen per acre. You compare to that the 200 pounds of nitrogen per acre for corn, and the first thing you said is, holy smoke, what's going on with all that nitrogen? And that's what we're here to tell you today. Why so much? The bottom line is there a lot of nitrogen is doing things. It's moving within the nitrogen cycle, not necessarily out of the biosolids pack, although it does eventually. And we'll look at the upcoming budget to get more specific about where. But in general, as trees grow, nitrogen demand increases, so the trees will pull more nitrogen out, and remember, it's a 6 or a 7 year cycle. Denitrification is very difficult to measure, and the estimates vary widely, but the conditions within the biosolids pack are really just about perfect for denitrification to occur. We've made some assumptions here because we don't have great numbers on hybrid poplar as a crop. We assume that the first year of steckings, new trees require about 55 pounds of nitrogen per acre. 6-year-old trees, on the other hand, require about 540 pounds of nitrogen per acre, and that's a number that was pretty well researched. So when we have trees that are older, we have a better handle on what they need. Denitrification is about, and pick a number between 1 and 40, and some research paper has probably stated that number. Anything above 10% has been found in denitrification on an annual basis. It was about 10% in some yards where there was about 7 to 14 days of denitrifying conditions occurring each year. So it got to be about 10% in just that 2-week period. 40% was some other work that was done on land that had gotten pretty well inundated with water. And so 39.6 is the number there. Because the conditions are so good, 39.6% is what I'm going to use. So this is that nitrogen budget I told you we'd talk about. If you have a starting nitrogen content of 14,132 units are pounds of nitrogen per acre, and the first year the crop uptake is only 55 pounds per acre. If the denitrification is going on at 39.6%, well, that's 5,500, almost 5,600 pounds. And so the remaining N out here is 8,480 pounds of nitrogen per acre. And so as we go down, taking this budget year after year after year, we find that by the 6th year, the remaining nitrogen is a negative 327 pounds, meaning that we didn't have enough nitrogen that last year to meet the plant's needs. Now that's assuming that denitrification cooks along at 39% every year. That's assuming that this estimate of crop uptake is pretty good. We think the estimate is not too bad. The denitrification we don't know a lot about, and we don't even know a whole lot about the conditions that go on underground in terms of seasonal variations. So this number is within the realm of possibility. Could it be less? Oh, certainly. We've done some research that indicates that maybe there's not going to be that much left. So yeah, this might be close, because we do find that the biosolids pack after 6 years is depleted down to the nitrogen that simply won't turn loose and come out. When we talk about monitoring this, and we monitored for research, but you monitor for permitting purposes a lot, we need to know about geology. We need to understand porous media flow, because that's where we're going to get our samples from. And we need to understand a little bit about nitrogen and phosphorus. The tools we use are lysimeters, interceptor drains, and wells. So that's sort of what we're going to talk about the rest of the day. So first, the geology. What is it that's below your feet? What is it? Well, we started with a sand and gravel mine. That sand and gravel mine, the gravel and sand are removed. We're left with the clay layer, and so we end up with something that looks like this. And littered on top of this clay layer, there's little tiny remnants of sand and gravel that you can see here. And you can see the sand and gravel remnants up top, and then the profile is mostly clay. So that's what we worked with at Erko. From the limited research we've done, we consider that just about a perfect condition for using DRE. We also need to know a little bit about the slope, which is called the dip in geological terms, of this geological layer in here that created, or that deposited, the clay. Where do we get our information about some of these geological formations? There's a couple of sources. One is USGS, and the other is, in our case, Maryland Geological Survey, or wherever you are, your state geologic survey. They have lots of reports of investigations, abbreviated RI. These are a couple of reports that I used on this, and you can see they're not exactly the newest stuff in the world, but thankfully the geology beneath your feet doesn't change a whole lot. So these are two of the major reports. There was two others that I didn't want to list, and you can find this sort of thing wherever you are. Almost all of them are available online now, so you just need to go into your geologic survey online and do it from your office. This is something that you can get from the Geological Survey, and it tells us what the geologic provinces, or the physiogeographic provinces, are. And we're on the Western Shores coastal plains, which is this yellow area to the left of the Chesapeake Bay. But the formation, or the geology there, is called coastal plains. This is another thing that you can get from your Geological Survey, and this is a cross-section of what the geology looks like underneath of northern Charles County. Well, southern Prince George's County is just above northern Charles County, and so our site is probably about 3 miles north of where this is portrayed. And that tells us that the formation just below the surface, and that superficial aquifer probably doesn't exist where we are because the sand and gravel has been mined out. And so we're looking at the top of the Calvert Formation when we look at what's on our reclamation site. And then there's a Nanjemoy Aquifer and the Aquia Aquifer and these little aquatards in between it. This is some writing that came out of it that describes that Calvert Formation. It's an olive gray to olive green micaceous clay silt. That's the key thing. That's the kind of stuff that won't let water move too fast. The thickness of the Calvert in the Waldorf area is about 90 to 100 feet. That's important also. So this comes straight out of the Geological Survey publications. You can also see water elevations. These are the water elevations. Typically, it's above mean sea level. So in this area here, you're looking at perhaps 50 feet above mean sea level, 30 feet above mean sea level. And that's just an arbitrary reference. There can be other references that are used. When we talk about monitoring, we think about two things. One of them is porous media flow. And I'll be talking about porous media flow quite a bit. That's how anything in the biosolids will leave the biosolids and move to the monitoring device through some sort of porous media flow. It could be saturated flow, where all the pores in the soil or the spoil or whatever we want to call that mix when we make it are completely filled, and Darcy's law applies. Darcy's law describes the flow. And I have little asterisks besides completely, because sometimes there will be some small pores that become air-filled, but that air is trapped in there, and so it acts just like another rock, and the water has to flow around it. So when I say completely saturated, sometimes it isn't completely, but if you're very deep into the water, it is complete. Unsaturated flow, that's where the pore space is occupied by water, air, both, and it changes with moisture content. There's something called Richard's equation, which is much more difficult equation to deal with, that describes flow in unsaturated conditions. Thankfully, we don't need to do anything with Richard's equation. We can use Darcy's law occasionally, and we'll talk about that just a little bit. Hydraulic head is a term that we use, and in fact, we just saw a map of it. If you map a whole bunch of hydraulic head, that's called a potentiometric surface, and that's what contour maps of water elevation look like. When we say water potential, that's not hydraulic head. That's hydraulic head plus some other stuff. There's something called elevation, and that's part of hydraulic head, but pneumatic pressure, water pressure, osmotic pressure, and thermal pressure, or potential, all contribute to water potential. If the media is saturated, there's no capillary effect, so there's no capillary pressure. If the temperature is fairly consistent, then there's no thermal potential, and typically there's no pneumatic pressure, which is air pressure, imposed on groundwater flow. So when we're saturated, that leaves the height of the column of water and the elevation. Those two things together make up hydraulic head. When we look at hydraulic head, we're looking at the sum of the elevation of the well, really the bottom of the well, above mean sea level, or truthfully above any other arbitrary mean, so long as you use that same common elevation in all your calculations. So you could find the lowest well in your mass of wells and use that elevation as Z equals 0. And so other wells would have a Z component to them and an H component. But Z plus H is the hydraulic head. It's the H, small h, is the height of the water in the well. Z is the elevation of water above some arbitrary datum. We call it mean sea level generally. So the hydraulic head is capital H. It's lowercase h plus Z. The gradient is the difference in those hydraulic heads. And that's what causes water to move from one place to another. Water flows just like gravity takes you downhill. Water flows from locations of high hydraulic head to locations with lower hydraulic head. The gradient is the change in hydraulic head divided by the length of the flow path. Maps of hydraulic heads, I'm going to show you a figure below. This is a map of hydraulic heads. We call it a potentiometric surface. If we look at these 2 points A and B, I can estimate the hydraulic head here as about 1,000. And I can estimate the hydraulic head here. If I trace this thing up here, and it's about 1,100. And so I have a change, a difference between these two. And I can take this scale here, run that distance between the two, and I can get a gradient between those 2 points. And you can do that any point on this map, and it gives you an idea of how something will move. You'd like to do it at right angles to this line and this line, because that's the way the water is going to move, 90 degrees away from a line of uniform potentiometric value. There's something called a Vadose Zone. That's the zone just below the ground surface. It's seldom saturated. We just had a gully washer of a storm, and the saturated zone probably didn't make it down 6 inches. The unsaturated or Vadose zone controls the rate of aquifer recharge. So what goes on in that zone is pretty important. Flow rates and chemical reactions in the Vadose zone control whether, where, and how fast contaminants enter the groundwater supply. So if we're getting water that's just zooming through the Vadose zone like a coarse sand, it's not going to be exposed to a contaminant very long, and the concentration in the water is going to be lower than if it moved through that Vadose zone slower. Our DRE trenches are installed in the Vadose zone. Monitoring for Felton transport of constituents in the biosolids is indicative of the processes that occur in the Vadose zone, but that's in our case because we put our monitoring into the Vadose zone, and we'll show you those in a while. Most wells, groundwater wells, are in the saturated zone, and so they're not in the zone where all the action is. This is ye olde nitrogen cycle. I think each and every one of you have probably seen some picture of it in which we see nitrogen in the atmosphere is changed into some other form by nitrogen fixation in a plant, and there are nodules in the roots that have bacteria in them that take N2 and they change it to a nitrogen form that the plant can use. Those plants die, and we have crop residue, and all of that becomes soil organic matter, which includes nitrogen. That can become nitrate, that can become ammonia, and then ammonia and nitrate have their own pathways. Fertilizer can be made up of nitrate and ammonia, and so ammonia can go into the soil from fertilizer. Manure can contain both, the same thing. And then with ammonia, we have soil particles that attach ammonia because it's got a positive charge. Most soil particles have no charge or a negative charge. That ammonia can go into nitrification and change to NO2 nitrite, which changes very rapidly in the presence of water to nitrate. Nitrate can go back to nitrite and get up into the atmosphere through denitrification. NO3, it takes some special things for that to happen for denitrification, but it can leach just in the presence of water. So those are the fates. I always have a hard time with these cycles, so I kind of write them down for myself and look at the things and see what's special about each step. We have mineralization, nitrification, ammonification, denitrification, and volatilization. Mineralization, that's nitrogen changing from organic materials such as biosolids, such as manure, plant materials, to an inorganic form of nitrogen that plants can use. Mineralization makes ammonia, NH3. The NH3 in the soil then reacts with the water to form NH4. This ammonium is held in the soils. Mineralization requires microbes. Mineralization is done in an oxygenated or an aerobic atmosphere. Nitrification, the ammonia in the soils is converted to nitrite and then to nitrate. So the end process of nitrification is NO3. Microbes perform both of these conversions, and these microbes require oxygen. Without oxygen, you don't get nitrate. Remember that. What happens to NO3 and NH4? Both of them can be taken up by plants. Annual plants take up nitrate easier than they do ammonia. Most trees are very happy to get ammonia. NO3 can leach. NH4 will move into the soil and get bound by the soils, so NH4 doesn't leach so much. Both of these can be consumed by microbes and become part of the microbes' bodies. So we call that step immobilization. Soil bugs pull nitrogen from the soil, and when the residues of decomposing plants don't contain enough nitrogen, when microbes take this ammonium and nitrate in, these forms of nitrogen are no longer available to the plants, and they don't go anywhere. This can cause nitrogen deficiency because while the ammonia is there in the soil mix, it's bound up by the microbe bodies. Denitrification is when nitrogen returns to the air as nitrate. As nitrate is converted to atmospheric nitrogen, N2, by bacteria. Incomplete processes like this create NOx's, NO and NO2, nitrogen oxide and nitrogen dioxide. Anaerobic microbes are involved in this, the lack of oxygen. These microbes also require a good carbon source to function. So these are things that I think of as important conditions. With monitoring tools, we have lysimeters. These are for the Vadose Zone. A pan lysimeter is also known as a zero tension lysimeter. And basically, it's a little pan like this green triangle down here. It goes beneath some source, and it's connected to the surface by a tube that you can use to pull the sample out. In our case, we put it directly below the biosolids trench. It was 30 centimeters below the trench, or 12 inches. And we put it there, backfilled, and used this to collect pretty free water. It was not really under any capillary tension. So this water moved pretty freely, pretty rapidly. This is the installation of a pan lysimeter. This is a Lysimeter Pan. It's upside down right now. This screen goes on top of it, and a plain old window screen made out of nylon goes on top of this. And then the whole thing is slid into this slot that we drill on a bed of sand, and the bed of sand backs up underneath this until the bed of sand actually presses this lysimeter up into the top of this slot we've built. And so we have a long drill with a tool on the end of it to take out chunks, and then we square it off with a very small trowel and a lot of hand moving. So this is what the slot looks like. After we get it installed, run the tubes up through the PVC and get ready to close it up. Forgot to mention that this trench is dug about 5 or 6 feet deep, right beside a trench of biosolids that's already been installed, and it's about 12 inches from here to the biosolids trench inwards. The biosolids trench quits right about 12 inches above this slot. Okay, other tool, suction lysimeters. Suction lysimeters work in a vacuum within this tube here. This is a PVC tube. This is a ceramic cup at the bottom of the PVC tube. The ones that we used were 2 feet long, but you can get them 6 inches long, up to 5 feet, and maybe 6 feet long. So you can get them almost any size. You can get them with 1 tube or 2 tubes, depending on where you're working. I always use the 2-tube variety for a couple of reasons. The 2-tube pushes water up through the second tube. It pushes it up a lot less turbulent than if you're sucking it up through the same tube. With the turbulence comes air entrainment, and some of that might have oxygen in it. Pardon me. So we don't want that oxygen stirred up inside the sample. We'd like to get the sample out with as little disturbance as possible, and for that reason I use 2-tube variety. These things ain't cheap. They're probably $300 a piece right now. And so we had about 150 of them in there. That got kind of expensive. Below this, we put in lysimeters that were 15, 30, 60, and 122 centimeters below the bottom of the biosolids trench. We also put them out to the right and the left, 15 centimeters and 30 centimeters, so that we could look at vertical flow away from the biosolids pack. This is what it looks like purchased and assembled. These are the two tubes, and they connect to the surface. Whenever you install one of these, you make a pack of mud, pretty damp mud, put it all over the ceramic cup, and install that into a hole that you've dug with a plain old hand auger. And that's the installation process. Backfill with the same soil that you took out of there, and then backfill all the way up to the top, doing a little bit of compaction as you go to make sure it's close to the density that it was before. There's another monitoring tool called an interceptor drain, and I don't have great pictures for that. But basically, wherever you have a boundary, like this boundary here, between two types of soils or between one geological element and another geological element, where this lower geological element is more impervious than the upper geological element, you can run interceptor drains along perpendicular to the direction of flow of water. So you need to know what direction the flow is moving, and that's what those potentiometric maps can help you find out. You can drill wells into the surface yourself, measure the height of water in those, and you can determine the potentiometric surface really, really roughly with only 3 wells drilled in a triangle. A triangle should be probably a half a mile apart from each well, but if you get values of elevation from there, you can get the direction of flow with only 3 wells. So the more impervious materials are below the less impervious. A trench can be dug into this more impervious material, and then a drain tube, plain old corrugated plastic tubing, can be put in here with an outlet to the surface somewhere. And so that intercepts all the water that's running down dip here. It'll intercept it here, and you can take it in as a long sample. It's great that it covers a much bigger upstream area. The media can be, this media above can be porous media, like sand and gravel or clay, or it can be broken rock, like the spoil that you get from coal mines in rocky areas. This is used in drainage experiments on coastal plains a lot. It was used on a mine spoil in Kentucky, but they installed this before the spoil material was deposited back on the more impervious material. That is, the material that was never blasted out, because the coal used to lay above this level. So you have to think ahead if you're going to do it in that broken rock spoil from mining where you have to blast rock away to get to the coal. In a porous media, a monitoring well is just a simple well. There's a lot of things in this diagram. There's a cap that can lock. That's important for the integrity of the sampling and for the chain of possession, so that you have belief that nobody contaminated your well. There's a little concrete base poured. There is backfill material. Usually this little transition seal is just bentonite, and this is some sort of sand or gravel pack around the well screen. That's pretty much the anatomy of a monitoring well. Well drillers drill these and put them in a lot, so it's not something they're not used to doing. You can get somebody that's familiar with putting in monitoring wells fairly easily. Broken rock's a different character. There's something called a percussion method of drilling. Sometimes it's called cable tools, churn drills, sputter, either TT or DD, I've seen it spelled both ways, or pounders. But these are one of the oldest cutting actions utilized in the drilling industry. This was used in China centuries ago. It's a method of drilling whereby an impact tool is suspended in the well from a steel cable and then dropped. Repeat as necessary. Then the stuff, the chips that it takes out, is brought to the surface, and then they build back up and start drilling some more. This is necessary in a broken rock kind of environment because a rotary drill will break the tool off almost every time where you have broken rock. When you start drilling down with a rotary tool, there's going to be more force on part of that tool than there is on the other because of the unevenness of the broken rock, and sooner or later that cable tool or that rotary drill tool breaks off. You can end up going fishing for it or having to start a new hole, but rotary drills and broken rock don't mix well together. This is just an illustration of one of the old Chinese cable tools where the cable was reeled in, sometimes by hand labor, and then it was released, and this weight would drop down in the hole, have an impact down there, pull up the chips, and repeat as necessary. This is what a more modern cable tool looks like, with a heavy steel weighted tool that goes down into the hole to the bottom. The impact is from dropping it from its own weight, and then it's pulled back up. A little bit about permits. John, we're ahead of schedule, so you can begin to get ready. A little bit about permits. In Maryland, because of the high loading rate that we're using, MDE can write many different monitoring requirements into the permits. There's no guideline for permits with something above, I believe it's, I think it's 50 tons, dry tons per acre is the limit. Anyway, it's a large number to begin with. But if you're higher than that, which we were, then you don't have any limits on what can be put into the permits. And the permits are written to try to get the agencies the information they think will be the most useful to them. Well data is easier for permitting agencies to evaluate because they're more familiar with it as compared to lysimeter data. MDE will work with you when you talk about monitoring. I don't think they're allowed to is why, but they won't tell you where to put a well. Rather, you have to propose a monitoring plan and they will approve it or deny it. So there's a little bit of work around there, but you do have an agency that will cooperate with you on trying to guide you the best they can without telling you explicitly, here's what you should do. Because they want you to write the monitoring plan, not them. Our Erco permits included some metals, total nitrogen, total phosphorus, ammonium, NO3, sodium, magnesium, copper, and some other stuff. Copper's a metal. There were some other metals in there. It included measuring foliar nutrient content, foliar leaf nutrient content. It included digging up biosolids from the pack each year and sampling for nutrients there. So this is what I mean when I say a wide range of things can be in your permit. Of course, each state agency is different, and they will have different thoughts about it. Okay, some results from the monitoring, and this will talk a little bit about how nitrogen can move. First is a sandy soil, and then we'll talk about the clay soil at Erko. The sandy soil was a mineral sand. It was ilmenite and zircon at a mine reclamation site, Dinwiddie County in Virginia. It was instrumented with pan lysimeters. Both anaerobically digested and lime-stabilized biosolids were used, and also inorganic nitrogen fertilizer were compared, as well as no treatment at all. So there was a control and a fertilizer, and then some DRE treatments. In terms of ammonia leachate, this is May 6th, 06 through December 08, just a little more than 2 calendar years. The concentration of nitrate in the leachate from the deep row biosolids ranged up to 400 milligrams per liter of ammonia nitrogen. And you can kind of see there probably was a seasonal effect here and a seasonal effect here. And you can see as time went on, it also diminished with time. But that's a pretty good high amount. If this got loose in a stream in any great volumes, it could really turn fish belly up in a hurry. This is organic nitrogen. The organic nitrogen went up to as high as about 540 milligrams per liter. This occurred before fertilization. This triangle is lime stabilized or blue pane stuff, and the fertilized is the little stars down here, and the control is also down here. So you can see that the biosolids had much higher organic nitrogen than the fertilizer or the control. Of course, that makes sense. There's no organic nitrogen in fertilizer, so you wouldn't expect it to show up in here. Now, there is ammonia and nitrate available in different fertilizers. And so you could see these X's are fertilizer nitrogen, and they went up, and in fact they increased from the first year to the second year. But again, the biosolids in both forms had a lot of nitrogen in the form of nitrate in them. 1100 milligrams per liter is just a huge concentration of nitrate. So what we can take away from this is that the total N lost over the course of 2 years was about 15.2 megagrams per hectare. I'm sorry I didn't convert this one to pounds per acre. And 10.9 milligrams per hectare for lime stabilized and anaerobically digested biosolids respectively, or 50% of the N applied, in other words. Entrenchment of biosolids in coarse textured media just shouldn't be done. Remember, this was a sand. In fact, it was kind of a coarse sand. This was the tailings from a mining operation, and so all that was left was the sand. It's not a good mineland reclamation technique with coarse sands. So that says that DRE has the potential to pollute. So to all the regulators out there, make sure you understand the soils that it's going on. This is from the last one where I talked about the importance of clay. You want some clay in your subsoils or in the soils that you're working with when you apply DRE. We did it to a sand and gravel site in Prince George's County. It was instrumented with plan lysimeters, suction lysimeters, and we also had monitoring wells surrounding the site. The lime stabilized DRE from Blue Plains was compared to no biosolids application and also to trees and no trees. Hello, there we go. This is one of the results. This is for pan lysimeters. The nitrate concentration in the first 2002 through early 2005, that's 2.5 years roughly, was pretty much nothing. We did see nitrate at this one time for one sampling in the heaviest rate, 13,200 kilograms of nitrogen per hectare. We'll talk about these numbers later. These are actually low by a factor of about 3.5. So this is actually around 1,200 and 2,400 and 3,600. So by year 3, we were beginning to see some spikes once or maybe twice in a row, and then it would drop back down to pretty low numbers. But those spikes were in the neighborhood of just 10 milligrams per liter, which is the drinking water requirement. You cannot have wells that are pumping greater than 10 milligrams per liter. It becomes a health issue. But this is in the soil, in the Vadose Zone, which is not really regulated. So we don't have a good standard to say what it should be in the Vadose Zone. However, this is the best guidance we have. So if it never goes above 10, then we're always happy. This is ammonia. This dark green is the heaviest level, this orange is the medium level, and this magenta is the lowest level. And you can think of them as 4,400 times 3 kilograms of nitrogen per hectare, or just think of this as 172 dry tons per acre. The orange one is 345 dry tons per acre. And this is, come on, I need my cursor. There it is. The green one here is about 610, I believe it is, kilograms or tons of dry biosolids per acre. So it is pretty nicely in the order of 1, 2, 3 right here. And right here it's in the order of 1, 2, 3. And in between it bounces around a little where this heavier layer is actually lower than the medium layer. One of the reasons we think this is that in order to get this heavy level, we had to dig our trenches so deep that it took a long, long time for the roots to get down to the bottom of the trench. And those roots were necessary to release the nitrogen. And you're only seeing that occur in 2007, maybe some of 2006, where there was a higher nitrogen release rate in the higher application, simply because the biosolids were buried too deep for the microbes to get down, or for the roots to get down there, and the roots provide oxygen, and oxygen is what makes the mineralization start. And the leg bone's connected to the thigh bone, and so on. Now, if we look at that ammonia in the suction lysimeters, this is talking about application level. Now let's look at the ammonia distance. This top line, this highest level of ammonia in the soil, is 15 centimeters from the trench, and this is directly below it. This next level of ammonia in the soil is 30 centimeters from the trench level. Now the 60 centimeters from the trench level is this level down here, and it's getting farther. As it gets farther away, 60 centimeters is approximately 30 inches, 36 inches. So this is 3 feet away from the source. And at 3 feet away, it's already cut the concentration level from, let's call it 2200, down to 200. Oh, that's a factor of 10, isn't it? So the distance away makes a big difference. Basically, the ammonia is being bound to the clay in that spoil or soil. If you look at it laterally, 15 centimeters is usually higher than the low level of 30 centimeters away. So you get a distance laterally also where that is being immobilized by the clay in the soil. Okay. What is the nitrate concentration in the suction lysimeters as opposed to the pan lysimeters? This is where there's capillary pressure affecting it. Well, from application in 2003 up to 2005, there wasn't any effect. And then we start seeing effects, and it's running up towards 10 and even above 10 once or twice. The reason that we're not seeing anything for a while is that the roots have not surrounded the biosolids pack and brought the oxygen into it so that nitrate could be formed from the organically bound nitrogen. It needs oxygen for that nitrification step to occur. And so until the roots of the plant, the hybrid poplar, bring oxygen down to the biosolids through a form in the plant called an parenchyma, which you can think of as a tunnel for air, you don't get formations of nitrate, and so you don't see it for the first 2 to 3 years. And then you see nitrate forming, and it's coming out into the soil at levels of between as high as 10 and once as high as almost 16 milligrams per liter. Remember, that's in the soil. So let's keep that in perspective. Remember, as high as 16 milligrams per liter. Nitrate in corn. If corn is treated with no fertilizer, you find nitrate in the water beneath the corn in 3 to 10 milligram liters of nitrogen at that level. In commercial corn, you have 18 to 30 milligrams per liter. In a corn-soybean 2-year rotation, that drops down to 23 milligrams per liter. In a corn-soybean 2-year rotation with cover crops and split applications, that should be 10 to 12 milligrams per liter instead of 110. So there's a typo in there. That should read 10. And so as you use more conservation methods, you get the concentration down to between 10 and 12. Well, if you look back, this is between 10 and 16. And so nitrate in corn is greater than nitrate beneath the biosolids in the DRE system once you get conventional corn. If you look at that and then look at nitrate in deep row trees, you can compare it on a time basis. And in March through June, we had 0 to 1. In June through April of 06, we had 1 to 10. And in April of 06 to November, we had slightly less. So we have low nitrate coming out into the soil in the first place. So conclusions on the Erko study in clay. For the first 3 years, 0 nitrate left the deep row tree system. Ammonium was immediately released into the soil surrounding the biosolids, but the transport wasn't very far away. The concentrations decreased dramatically with distance. After 3 years, the nitrates begin to range between 15 and 36 milligrams per liter, with the exception of 2 data points in the winter of 2008 through 9. Overall, nitrate concentrations are lower than those found beneath corn crops, but they're utilizing a great deal more application, or more of a higher nitrogen application. So I'm going to have questions in a minute, but I'm going to go way back to a slide way earlier. Look at the amount of denitrification that's occurring here. The crop uptake is never huge, but there's a lot of denitrification going on. So that's where a lot of the nitrogen is going off. This is not normally the case in cropping soils, because normally in cropped soils, everything is in an aerobic condition, and that's not primed for denitrification to occur. In the anaerobic condition, denitrification is just in a prime condition. And so that's what we see as the big difference, denitrification occurring. It's not something we think about. It's not something that's easy to measure. So I'm going to go back to the last slide, and we can begin to look at the chat room for questions and comments.
I want to thank everybody for attending. And as Andrew mentioned, these recordings are posted on our website. So if you really encourage you to share this with other people, and we'll, and what I put in the chat box is an evaluation. We really appreciate you filling that out to give us more information about if we did any more future programming or anything that give us an idea of what your interests are. So with that, I'll just let Gary maybe field some questions.
Okay. I haven't looked in the chat box yet. It looks like the only thing in the chat box is your one, is your Qualtrics survey.
Yeah, so far that's all we have. Everyone obviously has had all their questions answered by your commentary, so we will hang on for a little bit just to make sure no one has a question that comes up.
We put a lot of material into this last presentation. Thankfully, this should be available. Jonathan, I'm going to try to make this slide deck available. So just the presentation by itself will be available as well as the video.
And I guess I would just say that, you know, Gary talked a lot about the whole nitrogen side of it. And again, like I think I made the point that this whole system is dependent on that there's an adequate stock of the trees that's going to be able to fulfill that uptake by the plants, so by the trees, which is the forestry side of it.
And those things are intimately connected. Without those, lots of experiments were run with corn, which isn't deep rooting or perennial, and they lost their nitrogen out of the soil instead of going away as uptake.
Okay, we do have a comment thanking you for the denitrification table. The table that you provided today in the presentation, which isn't in the 48-page guide apparently, is really interesting and very helpful in explaining nitrogen fate.
Well, I will try to clean up that table just one more step. There was something else I didn't put in there, and I want to include that and then clean that table up and make it available. I'll probably just replace it in the slide set, and so you can go get the slide set and get it. I'm glad you appreciate it. It tells the story pretty clearly, but a lot of people that were in permitting just did not want to believe that denitrification levels could be that high. There was a research paper done by Taylor, and he showed that denitrification was very high, nearing those levels of 40%. And that was in a research setting in somebody research basement in the, I think it was in the Smithsonian in DC.
Okay, we have another chat room entry asking for your thoughts on lime stabilized versus anaerobically or aerobically digested for DRE.
There are pros and cons to both types. The DRE has a drawback in that its pH is 12. When the biosolids come in, it's pretty toxic to roots. And so that pH has to be dropped down simply by water and interaction with soil before the roots can infiltrate. We had a slide that I didn't show there. And I can resurrect that slide, so I think I'll just do that to help answer that question. This root has grown around the trench, and you can see how it's almost rectangular in its growth. And that's about 42 inches from there to there. And then later, in terms of time, the roots begin to penetrate down into down into the spoil. These roots penetrate in, and as they do that, they're dewatering the biosolids. Remember, the biosolids are 75% water when they go in, and these roots are dewatering it. It actually starts to collapse the soil above it. And so the nitrogen is taken up from the boundaries of the biosolids. It's only very much later where the roots penetrate all the way in. Here you can see what the remnant looks like when a trench is cut across the biosolids. It's much smaller than 18 inches. And of course the soil, what's left is pretty black soil, but it's very crumbly and very much mineral soil. It's really just been stained by the biosolids. Okay, we can escape from that. And I'll quit sharing again.
Harry, I have a question maybe for you about this. You know, you talked about the need for clay component in the soil.
Yes.
Is there some like minimum level of clay, percentage of clay that you have in mind? I mean, I guess you have big rocks and stuff. Everything, you know, changes. But I just asked the question because some people might be thinking that.
Yes, there is a minimum level, theoretically. Because we only have this one experiment, we can't tell you what that minimum level of clay is. So I'd love to have 3 or 4 different levels of clay, but we don't have that. So I know that you need clay. And if I can hazard a guess, and I can tell you that in that spoil where your hydraulic conductivity is less than 10 to the minus 5 centimeters per second, you probably have sufficient clay and sufficient packing. But that's being very general, using a hydraulic conductivity to substitute for clay minerals in the soil. And that's just based on my experiment with my experiment and Greg's. 2 experiments, that's all we got. Now, if anybody out there would like to fund some more experiments, we can work a way around that. This was, what this cost, about $1 million when it was all said and done?
Somewhere around there.
Yeah.
So, a place where you don't have that type of data is on some mine spoils per se, like coal mine spoils and stuff.
Yes, I'm very, very nervous about putting this on broken rock coal mines. However, if the coal mine operation can accept that there'll be some nitrate lost into the groundwater in the coal mine area and trade that in for the many benefits that you get from having a surviving and a stabilized habitat with trees, then that loss can be tolerated. It all depends on what that particular state thinks about losing some nitrate and ammonia maybe into the waters underneath a strip mine. I can't make those judgments, but you're going to get a trade-off. There's some numbers that you can use from Greg's paper that when I first presented the sand, you can probably get and expect the same numbers to occur from broken rock mine spoil.
Okay, we have a question. How did DRE biosolids pack pH change over time on the Erko sites?
We didn't do much pH studies. Once the biosolids were intact, we really didn't do it except for our annual sampling. And the pH dropped to around 8.4, around 8.4 to 8 point, somewhere in the neighborhood of 8 point something in the first year. And that's all I know. After that, it was in the high 7s, low 8s for the rest of the time. Remember, there's only an annual sampling of the biosolids pack. I think they took it in year 2, and then 3, 4, 5, and 6. I know they took it.
Okay, we do have another question. Matt from Schuylkill County is saying, how do you sell that to the DEP? And I'm sure that's a presentation in itself.
I believe that's Schuylkill, isn't it, Matt?
Yeah, that's what he's asking about.
Yeah, I thought that's how it's pronounced. In a strip mine area, you just honestly explain to them that there will be a trade-off for beginning to get your acid mine flow under control. You will have less acid water leaving once you have established this tree habitat. You will have considerably less runoff. You will have considerably less storm flow peaks, and you will have more infiltration, which will put more of the water into the subsurface. And it will avoid a lot of erosive loss from mineland soils. Those are the benefits of it, the habitat benefits. You have to sell all the benefits of it compared to the nitrate loss. And you just got to honestly come out and say, here's the drawback of this on strip mines. And what do you want? Acid water, or do you want some nitrate in the water as it turns to be less acid?
Okay, that is all we have at the moment. Oh, we do have a reminder from Jonathan to please fill out the evaluation. The link is there in the chat box. We would greatly appreciate your feedback about the entire series as well as the individual webinars themselves.
And I guess I would say if that, Gary and I are both willing, if you have questions and follow up, to send us an email.
Absolutely. We'll talk to you on the phone all you want. Email seems to be better now that we're trying to be social distancing, so I don't go into the office as much. But feel free to email me anytime. I see that several times a day.
And would you put the contact information slide back up there so people can see that one last time?
I will do that. Thank you for reminding me. I'm not looking at the chat any longer. If there's no further questions, I guess we should say thank you all very much for your time. We appreciate it. I hope that we've helped you a little bit. I'm sure I left you with almost as many questions as answers.
We will send out a follow-up too once all the recordings are up. We'll send out something to everybody to register about the direct link, and that's something you could share easily with others as well.
If you got this link from somebody else, you might want to send us your email to make sure that we have it, so that when we send these out, you'll get the follow-up information.
And that is all that is left in the chat box. So I believe we've covered all the questions so far. And once again, if anyone has your questions, go ahead and drop a line to Gary or Jonathan, and they'll be happy to discuss whatever they can share with you, and if not, point you in the right direction. Any final comments, gentlemen?
Thank you.
That's it. Thank you very much for attending.
Okay. Reminder that this has been recorded, and the recordings for all three of the webinars will be available through our website at go.umd.edu/woodland. Scroll down the homepage to the webinars and videos section, and there you'll find the entire series along with a variety of other webinars and videos that you may find interesting. So on behalf of Jonathan Kays and Gary Felton and myself, Andrew Kling with the University of Maryland Extension, we'd like to thank you all for joining us and enjoy the rest of your afternoon.